Hello everyone and welcome to today's webinar, Wood Frame Shear Walls and the SPDWS. My name is Marcy Weber and I'll be the education team moderator for today's presentation. Today's webinar will run 1 hour. Today's speaker is our very own Phil Line, Vice President of Codes and Regulations. This course is copyrighted and not eligible for reproduction. The American Wood Council is a registered provider with the American Institute of Architects Continuing Education Systems. If you are a member of the AIA and want us to report your credit for you, please email us after the webinar. Please note that this webinar and associated slides should not be used as a substitute for competent engineering support and expertise. Here is the team providing this course for you today. Again, your speaker, Phil Line, and behind the scenes, we have our engineering moderator, Lori Cook, Director of Educational Outreach, and then all things education and certification is provided by both Kim Paulson, our Education Administrator, and myself, Marcy Weber, Manager of Education and Accreditation. And with that, I am going to send you over to Phil Line.
Thank you. This is wood frame shear walls and special design provisions for wind and seismic, insights from testing with 10-penny short nails, varied end post details, and added gypsum wallboard. And the course description, 10-penny short nails in shear walls, shear wall end posts, varied shear wall end post details, and gypsum wallboard contribution to shear wall strength and stiffness will be summarized in this program. Also, we'll see results for walls sheathed on 2 sides and shear walls tested with applied vertical load in combination with shear loading. The objectives are for the viewers are to recognize select SPDWS provisions for design of wood frame shear walls, to be able to describe wood frame shear wall behavior under cyclic loading, identify shear wall detailing that provides better performance, and identify typical wood frame shear wall failure modes. The 2021 special design provisions for wind and seismic, you'll hear me refer to that as SPDWS, is the current edition. Sheathed wood frame shear wall requirements are in section 4.1 and section 4.3. And the SPDWS is referenced in the 2021 International Building Code. So this slide depicts elements of a sheathed wood frame shear wall. The elements, a typical wood frame shear wall test, often referred to as a benchmark wall test, are wood studs at 12, 16, or 24 inches on center. And in this case, 16 inches on center is shown. Wood structural panel sheathing, OSB or plywood, nailed to wood framing, top plates and bottom plates. And in this case, we've got double top plates. Typical wood frame shear walls have elements at wall ends designed for overturning, and in this case, we've got double end posts and conventional hold downs on inside face of post shown. And then typical shear wall will have connections at top and bottom to transfer shear wall shear forces. And at the bottom of this wall here, you can see anchor bolts that are typically used in testing. So here's a video of the cyclic behavior of an 8-foot by 8-foot shear wall test. And that video was showing the final stages of the test where gaps started forming between wall panel and framing, nails withdrawing and nail heads pulling through the sheathing and edge. And the data we collect is what is shown here in this graph. We're going to be seeing this kind of graph a lot as we go through the program. And so I'm going to kind of step through the different pieces here to kind of reduce the need to explain it later. So the y-axis is the load in pounds, and this graph is showing a range of roughly minus 20,000 pounds in that negative excursion and positive 21,000 pounds in the positive excursion. The x-axis is displacement inches, and shown here is kind of a range from minus 8 inches to plus 8 inches. The hysteretic response is shown in purple, and that's really tracing the top of wall displacement as the wall is being cycled back and forth. The average backbone is shown in red, and it represents the average bounding value of the positive and negative excursions of the hysteresis. And because it's an average response, you can see it's not really enveloping that positive excursion, because the positive and negative hysteretic excursion, they're not symmetric. And so this average response is always less than the best possible response we might get in one excursion or the other. In testing I've seen, usually that first excursion in the positive direction is the superior response. And this graph is showing a solid horizontal line at the top. And this represents a strength of 3 times the allowable seismic unit shear for the shear wall construction tested. Okay, so in this case, the 3 times value is roughly 21,000 pounds, and you can see the hysteretic response and the average backbone response are right around that 3 times value. Now, this hysteretic response and the average backbone really are representative of good behavior we expect out of a nailed wood frame shear wall. It's keyed to why the seismic R factor is R of 6.5 and ASCE 7. And analytical studies will take this kind of behavior and rationalize that the R of 6.5 is appropriate or not under certain conditions. So there's a lot of action going on in the front part of that curve, and this illustrates a lot of the back and forth cyclic moving happening in early stages that's not evident in that prior graph. So here we see back and forth cyclic loading, a lot happening in the early stages. And then the progression of loading as we get to bigger and bigger displacements. And then you can see this, the backbone that's shown is kind of tied to the negative and positive excursion and not the average backbone. So this photo is an illustration of what the testing to understand tenpenny short nail shear wall performance is about. We have the full-size tenpenny common nail on the right. It is a post-test view of the nail after it's removed from the shear wall, and it has bending in it. It's 3 inches long and it's 0.148 inch diameter. It is the nail specified in Table 4.3a of SPIDWS for shear wall design values. The nail on the left is called the tenpenny short nail in this study. That little black or the little brown plastic sleeve there is what's used to collate the nail. The short nail is 2¼ inches long by 148 inch diameter, so it's the same diameter as the common nail, full-size common nail. And this short nail is a relatively common substitute for the tenpenny common nail on the right. It's sometimes interpreted as equivalent. So the purpose of the testing that I'm about to describe was to see what the performance is of the short nail is when tested using nominally identical conditions as used in prior testing for the tenpenny common nail, that full-size nail on the right. So why do people think this short nail might be a substitute or equivalent for that tenpenny common nail? One reason is if you calculate the Z value per the National Design Specification for wood construction, the penetration of this short nail is adequate to develop the same lateral Z value as the tenpenny common nail. Also, Table 4.3a of SPIDWS had a column heading in 2015 and prior editions that used the terms minimum nail penetration. Because of that, some have interpreted that as meaning that a full-size nail is not needed for Table 4.3a design values of SPIDWS. And then finally, there's a thought out there that a shorter nail is less prone to create splitting in the underlying framing and potentially produce improved lateral performance compared to the longer nail, which might induce greater splitting. So in this test program, we tested 9 walls total, monotonic and cyclic. And the 2 major categories for breakout of results are whether testing was done using multi-story details. And we're going to see those later, but those are details that provide good overturning restraint, and other details that allows testing of the wall to large displacements. And then there's benchmark details. And those benchmark details have hold downs on inside face of posts and have been used on the majority of prior testing. The figures we saw earlier in this program were more like that benchmark detail configuration. So here's a drawing of the benchmark details. These were developed over time to represent a lower bound condition for testing of a code compliant shear wall to get a conservative strength and stiffness result. And so we're trying to get, a low bound strength and stiffness with this kind of detailing. Prior to this benchmark details where we're using hold downs to be more representative of end use, the majority of testing was using the ASTM E72 procedure, where rods were used, on either side of the wall system. And so these hold downs, conventional hold downs, weren't used. Other elements of this benchmark wall test is we have a flexible load beam at the top, hold down on inside face of post. The hold down is sized to match the overturning design requirements, so there's no over design in the hold down. The number of anchor bolts is the minimum per design using NDS provisions. There's no applied vertical load, and sheathing is attached with the sheathing nailing at the perimeter of the sheathing only. So where we have a 3-ply end post or a double top plate, the sheathing nails are in the outermost framing member. And the thinking is that the closer we push the nails to the edge of the sheathing and to the outermost framing, the more it would hurt strength and stiffness performance, because nails are near the edge of sheathing and they're aligned in framing members and could induce splitting related strength reductions. Also, it has been known that the hold down on the inside face of post gives lesser performance than other hold down placement configurations, such as hold down on the outside face or where you have end post sandwiched between hold downs. And so we'll see that a little bit later. I'll be referring to this kind of configuration as the benchmark details throughout the program. And so then here are the multi-story details. And these details had a completely different purpose than those benchmark details. And so the purpose here was to develop data that might be more representative of performance in end use conditions at the bottom of multi-story construction. That's 3, 4, 5-story construction. So we have a rigid load beam that may, better reflect the stiffness of the structural elements above this lower story wall. We have a rod overturning system. Sheathing nails are distributed to multi-ply posts that bracket the rod. Sheathing nails are distributed to each of the top plates. The anchor bolts are still the minimum per design using NDS. And there's top and bottom plate extensions that help reduce compression perpendicular to grain deformations. And, we feel that those are exaggerated in the benchmark details because all the bearing is happening at the end of a top or bottom plate. It's the bearing that happens from overturning of the end post. And in this detail, the top plate extension, why it's important is that we found that it helps us push the wall to bigger displacement. It helps brace the top of the wall as it rotates towards the sheath side as these walls get loaded to bigger and bigger displacements. And so here's a more granular view of the details. On the right are the multi-story details, where you see that 2-inch edge nailing is distributed to outer stud plies and to double top plates. And then you also see this rod system right here, rod system, and then distributed nailing to double top plates. And this edge nailing is distributed to the stud plies that bracket the rod. And then for the benchmark details on the left, you see the hold down on the inside face and all of the sheathing edge nailing pushed out to the farthest edge of the sheathing while still being at least 3/8 inch minimum edge distance. So stagger is specified here, okay, because that's a requirement of SPDWS when we have 10-penny nails at 2 inches on center. And then just for reference, that 10-penny at 2 inch on center configuration is the strongest configuration permissible under special design provisions for wind and seismic. And it translates to about 870 pounds per linear foot of allowable seismic unit shear capacity for a one-sided wall, or 1,740 PLF allowable seismic unit shear capacity for a two-sided wall. Part of the idea, a lot of the testing, I think all of the nailed wood structural panel shear wall testing we're going to see throughout this program is going to use this 10-penny nail at 2 inch on center configuration, the strongest configuration, And the idea here is to test this configuration to tease out possible weaknesses in framing, splitting effects due to closely spaced nails and large nails. And I think, by the time we get to the end here, we'll have probably over 40 tests in total with 10 penny nails at 2 inches on center. So here is a photo. The left shows the benchmark details and the right shows the multi-story details. Benchmark details are shown here and on the next few slides. Here we see the hold down attached on the inside face of the end post. Sheathing edge nails are pushed out to the edge of the panel, and that stagger is in place per SDPWS requirements. And then at failure of the benchmark details, we see rotation of the post and separation of the sheathing. If you look closely in the bottom right corner, you see a mixed mode of failure consisting of nail withdrawal and nail head pull through the sheathing. And then another view of damage for the short nail testing, under benchmark conditions. Nails are withdrawing, as well as push to bigger displacements or nail head pull through. You can project the nail pulling through the sheathing right here. This one particular nail decided to stay in the framing and the head pulled through, but you can see the other nails, there's withdrawal and the beginning of potentially some edge tear out modes going on. So for the multi-story details with the 10 penny short nails, here's a figure of the bottom of the wall. The rod is shown. Plate washers are shown in this figure, and they are per special design provisions for wind and seismic requirements. The minimum distance from plate washer edge to the sheathed edge is 1/2 inch per SDPWS, and that's maintained here in this study. And then here's a view of the adjoining panel edge nailing, and it's required to be staggered. And then at the bottom plate, we see the staggered nailing as well. And then here's a view of the wall near failure. It's hard to see here, but there's a gap forming at the bottom right corner. Again, this is much smaller than that blow up we saw in the benchmark detail, but we do get that corner somewhat dominating the initiation of failure. And the sheathing's prying up, and on the opposite side, we're not able to see as we're seeing it. There's going to be edge tear through, head pull through, and nail withdrawal. So here's a post-test photo of nails at the adjoining panel edge. Between both edges, we have about 100 nails in this joint. Remember, we're 2 inches on center nailing, and we got about 96-inch stud height or wall height here. Give us about 100 nails total. And again, we see a mixed failure mode, primarily withdrawal, but a mixed mode with some head pull through. One thing that's visible here that I didn't mention is, per SDPWS requirements, there's for this closely spaced nail high strength configuration, you can use 2 2-bys at the adjoining panel edge adequately stitched. And in this case, you can see the screws that are used to connect the 2 2-by studs at the adjoining panel edge. We've used screws and nails, all designed per NDS, and had good results there. We did have some testing recently where we used bolts, and we incorporated oversized holes in the bolts per NDS, and we had a little bit of extra movement there that really wasn't as good of a response as these nails and screws that give a better initial stiffness, load deflection performance. And then looking at the end of the wall, you can see nails remained in the framing in some cases. So the heads pulled through, or there was edge tear out. And then in some cases, the nails just withdrew from the framing. So here's an example of the nail that stayed in the framing, and it either pulled through, the head pulled through the sheathing, or tore through the bottom edge. Here's a picture of the short nail post test. In all cases, about 300 nails in this tested wall, there is some form of bending in the nails. So here's kind of a graph view of the benchmark results with the hold down on inside face. If you look at strength broadly, we're hitting about 16 kips and across the tests. And if you look at displacements, we don't have many readings past 4 inches, definitely not many past 5 inches of displacement. And then comparing to the multi-story details with rods, we get slightly better strength results, approaching 17 to 18 kips. but we're better able to generate results up to 8 inches of displacement. And so recall this wall is better held in plane with those top plate extensions, and the rod is doing a better job of holding the wall together. So looking at the 10-penny short nail results, comparing multi-story results and benchmark results, multi-stories in that upper grouping, benchmark in the lower grouping. One thing to keep in mind is when we do compare these results, drift capacity, peak load over ASD load, and ductility, all of the walls tested with short nails met ASTM criteria for seismic equivalency to the shear wall system prescribed in SPDWS. That is, the peak load over ASD load exceeded 2.5. It was 2.5 or more. A drift capacity of 2.8% of the wall height and ductility of 11. And so part of what's happening here is that the benchmark walls incorporate an 8% strength reduction in 2021 special design provisions for wind and seismic. So while the benchmark walls are weaker, because there's a design strength reduction in SPDWS for hold down on inside face of post, we come up with a similar peak load over ASD load ratio. So right here, we're seeing 2.5 that's similar to this 2.5 and 2.6 for the multi-story details. So one important point here is that this peak load over ASD load ratio, this column, is the ratio of the peak load from the short nail test divided by the ASD load for the common nail, because the 10-penny short nail configurations tested technically don't have an ASD load per 2021 SPDWS. So here we have the prior 10-penny common nail results. These are the full size nail results when tested under nominally identical conditions, multi-story and benchmark conditions. And you'll see these multi-story detail results are much better than associated with the 10-penny short nails. So right here, we're going to see this peak load over ASD load ratio significantly better than what we see in short nails under multi-story test conditions. Similarly, drift capacity is improved, and so is ductility. And here we see that the 10-penny common nail results tested with benchmark details had similar performance to 10-penny short nail results tested using the benchmark details. So graphically, the 10-penny common nail results from prior studies look like this. The magenta curve is for testing using full-size 10-penny common nails under multi-story details. And the black curve represents full-size 10-penny common nails using benchmark details. And you do see a big difference here between the boundary conditions for testing, multi-story versus benchmark. The black line at the top is that reference line of 3 times the allowable design capacity for seismic. And I'm showing this now because we're going to compare these 10-penny common nail results to the 10-penny short nail results that were tested under nominally identical conditions. So the reference line stays in place, and here's the 10-penny short nail with benchmark details. 3 cyclic tests are shown. Add in the monotonics for that case. And here's the 10-penny short with multi-story details. We expect this to be better, and it is. And then here's the monotonic for that case. And then here's the 10-penny common nails we saw earlier, and with monotonic added. So clearly the 10-penny common nails, full size, are exceeding strength and deformation capacity performance of the 10-penny short nails. A couple of comparisons to highlight are shown here. This 10-penny short over 10-penny common nail performance in benchmark conditions. That's the case with hold down on inside face of post. The performance is lower, but not drastically lower, about 6%. And that tells me that if we have test details that can't develop the nail strength, the difference between the short nail and the full length nail get minimized. For 10 penny short to 10 penny common nail performance in the multi-story details, we see more significant underperformance of the 10 penny short nail, close to 20% in strength reduction in the monotonic test. And so here's what I'm trying to refer to. Under benchmark details, right here, benchmark, we have about a 6% strength difference between short nail and full length nail. And then under multi-story details, there's about a 20% strength difference between the short nail and the full length nail performance. So in summary, we saw this on the prior slide when we're looking at the benchmark details. The 10 penny short nails had roughly 6% less drift capacity and strength than the 10 penny common nails, shear walls. And then under multi-story details, the 10 penny short nails had lower drift capacity and strength, approximately 15%. And it's based on this multi-story details. I think a recommendation is that if the short nail is being used, reduced design strength should be considered for 10 penny short nail shear walls. So how does the 2021 SPIDWIS address the 10 penny short nail? One of the changes that happened in 2021 SPIDWIS is that the table now lists the full dimension of the nails. And so we've got nail length, head size, nail diameter listed in the table itself. And that column that said minimum penetration has been replaced by a term minimum bearing length. And that tries to capture, use of a full length nail that might penetrate all the way through flatwise blocking. And then also 2021 SPIDWIS added commentary to indicate that short nails are an alternative to the full length nails. And the intent there is it should be looked at as an alternative method. And then so here's information from the commentary, and you'll see a lot of references pointing to data that will help guide someone that wants more information about short nail and full length nail performance. And then here's table 43A, an excerpt of that table. You'll see that column heading says minimum nail bearing length. That used to be penetration. And then in the nail size column, instead of just saying 10 penny common, it says 10 penny common, but it lists the full size, 3-inch length, 0.148 inch diameter, and 0.312 inch head diameter. And then in the far right here, we see 2435 nominal unit shear capacity circled. And you'll notice that's the highest nominal unit shear capacity that's in the table. Okay, shifting gears now to effective end post details. These details are arranged in order of increasing strength as we move from left to right. So for configuration A, testing has confirmed this is the worst case condition. It is the benchmark detail with hold down on inside face and all panel edge nailing in the outermost framing member. Configuration B, we simulate a solid ply end post, which is better than the far left condition. Configuration C, we have distributed nailing to each of the individual plies of the end post and hold down on inside face. And then finally, the best case is configuration D. It's the best case for strength, and that's where the hold down is on the outside face. So here are photos of basic configuration A, B, and C from the back side and on the left, and then configuration D on the right. That's the hold down on the outside face. Here's a photo post-test, 2 photos post-test. The one on the left is a post-test photo with the hold down removed. You can see the screw holes there from the hold down splitting that's happening in the end post. But the failure mode here was the sheathing separating from the studs and framing. And you can see that familiar gap happening between the sheathing and the frame here. And also we can see here the plate washers used in testing. On the right-hand side, we're looking at the end of the wall where nails are pulling through the sheathing, nail head pull through, edge tear out, and then a lot of fracture of the sheathing under cyclic loading. The panel gets progressively damaged more and more as we push to bigger and bigger displacements. So here are the 10 penny common nail results for configuration A. Adding in configuration B, simulating solid post, and adding configuration C. This is the distributed nailing to the multiply end post. Still hold down on inside face. and then configuration D with the hold down on the outside face, and it had the best peak strength. One of the things to notice is that while configuration D had this, you can see this higher initial stiffness and better peak strength, the deformation capacity was probably the best performance was observed by configuration C, where we had that distributed nailing. So there may be, a trade in performance here, peak strength versus deformation capacity between configurations C and D. And then just finally, as a reminder, that black line at the top is the reference line of 3 times the allowable seismic unit shear per spid width. So what does the special design provisions for wind and seismic say? Well, table 4.3a has a footnote to reduce design values for 10-penny common nail shear walls when the hold down is on the inside face of the post. And I'm going to read it here. Where tension force induced by shear wall overturning is resisted by a hold down attached to the inside face of the end post, nominal unit shear capacity shall be multiplied by 0.92. And so if there's a hold down on the outside face of the post or both inside and outside face of the post, this strength reduction doesn't apply, and it also doesn't apply for rod hold down systems. And the way this footnote is noted, and we'll see here on this slide, it applies to the 10-penny nail case. This slide is adding how to calculate the seismic unit shear capacity for seismic, both ASD and LRFD. And for this 10-penny nail at 2 inches on center, the nominal strength is 2,435 PLF. Divide that by 2.8 ASD reduction factor for seismic, and that's in section 4.1 of SPDWS, and you come up with 870 PLF. And that's if rod systems used or you have hold downs on both faces of post or the outside face. But if there's a hold down on the inside face of post, that 0.92 factor applies, and the allowable seismic unit shear capacity becomes 800 PLF. So now we're going to move on to gypsum wallboard contribution to shear wall performance. And there's a lot going on in this table. I think it describes 17 walls tested to understand the range of contribution of gypsum wallboard to the in-plane racking performance of wood structural panel shear walls. So there's test groups A and F. I know they're spread out on the table, but those are groups evaluating half-inch gypsum wallboard attached as a finish, and that is gypsum wallboard is not attached to the top plate. It's kind of floated up to the top plate area. And test groups B and E utilize 5/8" Type X gypsum wallboard attached as part of a fire-resistant rated assembly. And then test groups C and D, these are 10-penny common nails, the full-length ones at 2 inches on center edge nailing on one side, and 5/8 Type X attached as a fire-resistant rated assembly on the opposite side. So we get to see the combination of wood structural panel and that 5/8 gyp in those cases. And then test groups G and H, those are the bare frame tests with rod and no sheathing. So this is a figure that depicts those multi-story test conditions. In this program, studs were 2x6 and spaced at 16 inches on center. The top plates were 2x6, double 2x6, and we have that top plate extension. The wall bottom plate is also 2x6, and you can look closely, there's an 1.5 inch extension beyond the end of the wall, and that simulates extensions associated with door jamb conditions where jack studs are provided adjacent to door jambs. A rigid load beam is used. You see that at the top of the wall. Rod tie downs are used. And the sheath dimensions of the wall are 8 foot by 8 foot. The wood structural panel adjoining panel edge occurred over 2 2x6s connected with screws to transfer the shear force that happens at that adjoining panel edge. The shear wall test frame and boundary conditions are shown on the left prior to application of the 1/2 inch gypsum wallboard, shown on the right. This 1/2 inch gypsum wallboard was applied horizontally and attached with number 6 type W screws at 16 inches on center and not attached to the top plate. And I know that's hard to see here. And the horizontal joint was not blocked. Okay, here we've got the test frame shown on the right prior to application of 5/8 Type X gypsum wallboard shown on the left. That 5/8 Type X gypsum wallboard was applied vertically and attached with number 6 Type S screws at 7 inches on center. And screws are installed at top and bottom plates and all studs. And these are installation details associated with Type 8, 5/8 Type X to meet sound and fire requirements. And so here we have illustration labeled Figure 3. It depicts 1/2-inch gypsum wallboard fastening on the left. If you look closely, you can see the nails, and fastening of the 5/8 Type X wallboard on the right. For the 1/2-inch gypsum wallboard, again, no screws in the top plate, and screw spacing at other locations was 16 inches on center. And then for the 5/8 Type X gypsum wallboards, screws are installed in the top and bottom plates and all studs. And the spacing was 7 inches on center. So here are the graphs of cyclic results for the 1/2-inch gypsum wallboard in the uppermost graphs. And then the lower graphs reflect the cyclic results for the 5/8 Type X gypsum wallboard attached for fire resistance rating. And you see pretty stark difference in deformation, performance, and capacity. So peak capacity for that 1/2-inch gypsum wallboard was around 800 pounds. And then for the 5/8 Type X, we're seeing around 2,400 pounds for this 8-foot wall length. So this is the test of the nailed wood structural panel wall. We see here, this is the figure that was shown really early in this program, and this hysteretic response is showing peak load around 21 kips in that positive excursion, and we also see that average backbone drawn in here. These are with these full length nails now. And so this figure here depicts the load deflection plots for the gypsum wallboard and the bare frame with the tie rod system, the rod tie down system. Y-axis is lateral load in pounds. The x-axis is lateral displacement at the top of the wall. And the two solid lines in black at the top of the curve, we're going to start at the top and work way down, but the two solid lines in black at the top are the monotonic results for the 5/8 Type X gypsum wallboard. The two nearby dashed lines, also black, are the cyclic backbone curve. And the significant difference in displacement, peak load, drift capacity, and peak load performance can be seen visually here, but we'll also show that numerically later. And then below those two lines, those 4 lines in blue, are for the 1/2-inch gypsum wallboard test. The two solid lines are the monotonic results, and the dashed lines are the cyclic backbone results, average cyclic backbone results. And then below those lines are 4 lines in red, which overlap. So it may look like one thick line or maybe 2 lines. And they represent the monotonic and cyclic backbones from testing of the bare frame with rod tie down only. At large lateral displacements, we see the load continues to increase due to increased tension in the rod. And one of the things we see is, increase in load at large displacements of the rod and frame only starts approaching the 1/2-inch gypsum wallboard system at big displacements. They become asymptotic. So this figure depicts the load deflection plots for gypsum wallboard and the bare frame with rod tie down. At the very bottom of the plot, and results for testing 1930 seconds wood structural panel at the top, and those are with 10-penny nails at 2 inches on center. And just as a point of reference, all of the curves at the lower portion of this graph are the same curves we looked at on the prior slide, but now they're placed on a plot that has expanded scale to include wood structural panel and gypsum wallboard tests. So these are high strength wood structural panel shear walls with gypsum wallboard added. So starting at the top of the plot, these 2 solid lines and the 3 dashed lines of the same purple color are the monotonic and cyclic backbones for the wood structural panel on one side and 5/8 inch Type X on the opposite side. The monotonic results are approximately 20% greater in strength than the cyclic backbone, these average cyclic backbones shown here. And then the two solid lines and two dashed lines below it in gold are determined from a prior study for 19 30-seconds wood structural panel tested alone, and that is with 10 penny nails at 2 inches on center, under nominally identical conditions without gypsum wallboard on the backside. And in these gold curves, we see that the monotonic result is approximately 6% greater in peak strength than determined from the cyclic backbone. Later charts will show that the 5/8" Type X is approximately additive in strength to the wood structural panel under monotonic testing. And then under cyclic loading, the strength increase from gypsum wallboard is approximately 3% over that of the wood structural panel alone. One other observation is the drift capacity of this 19 30-seconds wood structural panel tested alone it does appear to be, there's a lot of scatter here, but it does appear to be greater than associated with the wood structural panel gypsum combined system in purple color. It's hard to see here, but I think we'll see in tables later when we average out numbers that might translate to 15 to 20% better drift capacity. So I've highlighted a few of the results in this table here. Drift capacity and overstrength results from wall C and D in the red blocks for walls with wood structural panel on one side and 5/8" Type X on the other side show that the monotonic results produce significantly greater drift capacity and overstrength than obtained from the cyclic results. So the upper row here is showing monotonic results versus cyclic results. That's drift capacity, so that's roughly that 20% I mentioned. Looks like a little more than that. And then peak strength, 3.4 versus 3. And then from wall A and B of a companion study that's highlighted in this blue box, and this is wood structural panel tested alone, comparing monotonic to cyclic. We again see monotonic results produce better drift capacity than cyclic. Here's 6.1 versus 4.5. And a modest strength increase, 3.1 versus 2.9, monotonic versus cyclic. Regarding the 5/8" Type X gypsum wallboard contribution, if we look at the red box, under monotonic loading, the combined 5/8" Type X wallboard and 19 30-seconds inch wood structural panel wall had 11% greater peak load and 19% less drift capacity than the nominally identical wall without 5/8" Type X gypsum. So here's the comparisons. Here's where we see that 19% reduction and the 11% increase right here. And then from the blue box, when we look at cyclic loading, the combined 5/8" Type X gypsum wallboard and wood structural panel sheathing had 3% greater peak load ratio and 11% less drift capacity. We'll see that here. And so, to summarize, what the testing showed is the bare frame itself provided small lateral resistance that didn't vary with load protocol and gave progressively increasing strength with increasing displacement. The 1/2" gypsum wallboard attached as a finish had modest racking strength and stiffness under cyclic and monotonic loading. And the 5/8" Type X gypsum wallboard racking resistance varied with load protocol. Peak loads were lower, approximately 11%, and occurred with less displacement, minus 49%, when tested cyclically instead of monotonically. And so there's a big difference in monotonic and cyclic results for the 5/8" Type X. And then the combined wood structural panel and 5/8" Type X. Under cyclic loading, there was a modest 3% increase in strength over wood structural panel tested alone. And, I think under cyclic loading also we saw reduced displacement capacity. And then under monotonic loading, the 5/8" Type X gypsum wallboard added initial stiffness and strength, approximately 11%, that approximated superposition of each individual material strength on top of each other. And so what does SPDWS say here? The relevant provisions are in section 43542, shear walls with dissimilar shear wall sheathing systems on opposing sides of common framing. And for seismic, this basic clause applies. The combined nominal unit shear capacity shall be taken as either 2 times the smaller nominal unit shear capacity or as the larger nominal unit shear capacity, whichever is greater. And so what happens in the case where we have wood structural panel on one side and gypsum wallboard on the other side, given the differences in seismic R factor, R of 2 associated with gypsum and R of 6.5 associated with wood structural panel, the common practice is just to not count the opposite side and use the R of 6.5 for wood structural panel alone. It would be permissible to, double the gypsum wallboard side and use that in design where you have wood structural panel and gypsum on opposing sides, but then that would be coupled with an R of 2 design for seismic. Now the exception here lines up with the monotonic results we saw, and the exception allows that for wind results or for wind design, that it's permitted to add the kind of sum the sheathing capacities on each side. So now switching over to a couple of other cases that where testing has confirmed SPDWS requirements. Here's a case where we've tested that 10-penny nail at 2 inches on center in single-sided wall test and two-sided wall tests. The lower two curves here are sheathed on one side, monotonic results, and then the upper configuration is sheathed on two sides. And that upper curve is truly the strongest unit shear capacity we can get from SPDWS for a two-sided sheathed wall. And then you'll notice that that black reference line there, that's the reference line for 3 times the two-sided design, seismic design unit shear capacity for the wall system tested. Okay, so that black reference line doesn't really apply to those lower curves. It applies to the upper curve. And you see for the two-sided wall test, we exceed that 3 times unit shear capacity expectation out of a kind of a properly configured and tested wall. And so what does SPDWS say about the requirements? These bullet points just summarize what I just went over. And SPDWS relevant provisions are section 4351, shear walls with similar shear wall sheathing systems on opposing sides of common framing. There's an equation here to account for stiffness, combined stiffness, and nominal unit shear capacity. And then stated simply in commentary, when you have this configuration with identical shear wall sheathing and nailing on opposite sides, we state that using the equations, a wall having identical construction on each side, e.g. a two-sided wall, has twice the capacity of a wall sheathed on one side, for example, a one-sided wall. And then finally, in a separate set of testing, that same 10-penny nails at 2 inches on center case was testing with and without applied vertical load. The orange curves here represent the configurations we've been looking at most often. That's without applied vertical load. And then the purple configurations represent an applied vertical load of approximately 2,000 pounds per linear foot along the wall length. And so what we see here lines up with our expectations from prior testing that applied vertical load is beneficial in tested shear wall performance. I think we see the improved initial stiffness and slight improvement in peak strength, and it is a modest improvement, but it's still an improvement. And I think I think something that's happening here is that extra vertical load is just helping to do a better job of holding the system down and delaying the onset of that sheathing uplift and prying damage that we see at the corners of the walls. And then in SPDWS, where's the SPDWS requirement for this? And there's really not a requirement that helps or hurts design unit shear with or without applied vertical load. But I thought this was the most relevant one. It's section 411 design requirements. And it's basically this, you kind of engineer the wall to provide to satisfy requirements for load path. So the frame, the studs, and a shear wall system carry the vertical load, and the sheathing and the nailing transfer the unit shear load. And as a lateral system, they're somewhat independent. While the sheathing nails and the sheathing help brace the studs, they're not relied on to carry the vertical load. That's happening in the studs separately. And this requirement here in 401 just kind of lays out that load path kind of design that we're familiar with for wood frame shear wall. The majority of what was summarized in this program is covered by these papers that have been produced over the years. The earliest paper shown here is from the 2008 timeframe, but since then, probably tested 50 plus walls, trying to understand these different effects that we're covering here. I think this program gets into roughly 40 plus walls results. And then finally, over that time period, we had the assistance of a designer industry task group that helped inform on what they thought was important to be tested and boundary conditions, etc. And those individuals are listed here. And then I wanted to thank everybody for your interest.
All right. Thank you, Phil. That was an excellent presentation. And we've had quite a few questions come in. So since we're getting close to the top of the hour, we'll go ahead and jump into those. All right. The first question is related to the shear wall tests. The question is, why are there double studs at the plywood splice in the shear wall test? Should the test have the sheathing spliced over a single stud, which is how walls are typically constructed?
Oh yeah, that's a good question, Lori. I didn't address that in the program, so let me hop here to the SPDWS requirement where that shows up. The adjoining panel edges in a shear wall are required to occur over a common stud, and there is a requirement in 4.3 in the shear wall construction section. I'm going to flip to it here, and I want to show what that requirement looks like. 4371, and it's 4371-5, and it says where any of the following conditions occur, the width of the nailed face of a common framing member or blocking at adjoining panel edges shall be 3-inch nominal or greater, and all nailing shall be staggered at all panel edges. And so the shear walls highlighted in this test were the high strength shear walls. They had nail spacing of 2 inches on center, which was also meets this requirement B, and then the unit shear exceeded 980 PLF. So the wood structural panel walls we tested definitely required this 3x at the adjoining panel edge and the stagger. But then there's a further requirement that allows, in lieu of a single common framing member, 2 framing members that are at least 2-inch nominal thickness shall be permitted where designed in accordance with 43611. And so there's going to be requirements for interstitching of those 2 2x to transfer the shear across the joint. And the SPDWS commentary has some information on how to do that. The method that was used in the testing that was shown, we basically run a calculation of what the 10 penny nail capacity is per NDS, sheathing to frame, and we make sure that the stitching of the studs equals or exceeds that capacity. Knowing that we have those 10 penny nails at 2 inches on center, the stitching of the studs needs to exceed that amount of capacity that could be developed in that nailed connection.
Mm-hmm. Great. We've had quite a few questions come in regarding nails and fastenings. So I think we might do a kind of combine a few questions into one. So the first one, this probably could be a shorter answer. Are there provisions for roof sheathing ring shank nails to be used in shear walls in the 2021 SPIDWIS?
Nope. So the for shear wall construction, 2021 SPIDWIS and prior editions address only two nail types: 10-penny common nail, which is the common nail, which is a smooth shank nail. And then if you get into the footnote here, there's a galvanized box substitution that's allowed for shear wall construction, but no ring shank nails are addressed in shear wall construction.
Mm-hmm.
And one of the issues there is that ring shank nail might alter, while the strength might be very good, it might alter that load deflection performance that we see out of a smooth shank nail.
Mm-hmm. All right. Another question on nails. So if the short nails achieve the published strength of the common nails, do we have to reduce the capacity, or shouldn't we be providing a distinction in SPIDWIS? So I guess some folks were looking for some more comments on, the 10D short versus the 10D common, and why, if it does meet that minimum required penetration, why there is the difference with the short nails like we discussed in the testing.
Okay. Yeah, so that's a really good question. And what we found was in some testing, the 10-penny short nail had equivalent strength performance to the full length nail, which is now, clearly prescribed in this table. This is the case that was tested right here. But we're dealing with a 10-penny common nail, full length, and sometimes that 10-penny short nail did achieve the same strength as the full length nail. But there were other conditions where we had better overturning restraint, where the full length nail was superior in strength and deformation capacity. And so it's not, under the full range of end use, it's not an equivalent substitute. And it's technically not permissible as an option under SPIDWIS. Someone may incorporate a 10-penny short nail in their designs, but that would be an alternate methods type of design.
Right. Okay, we've got time maybe for one more quick question here. Are there any provisions for screws?
There are no provisions in SPIDWIS for screwed shear walls. So it's very prescriptive. This table does a large part of defining the system, along with the remainder of Chapter 4, but it sets out the panel thickness requirements and then the fasteners that are needed. It's very prescriptive. So there's not an option in here for screws.
All right. All right, I think we'll go ahead and give it back to Marcy to close us out for today, since we're at the top of the hour. Thank you so much, Phil, for this really informative presentation. I'm sure we'll have to touch on this topic again soon based on the number of questions that we've had come in. I think we probably could do another hour.
This ends the American Institute of Architects Continuing Education System, and I hope you have a great day. Happy holidays.